Hello and welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're looking at the beginning of the next to last section we're going to cover. That's nuclear. There's a couple different terms that we want to go through, so let's start there. Nuclear is defined as a study of energy and reactions associated with a change at the atomic level. So what's that? I mean, at the atoms. Now, we need to know what something is radioactive. The substances that experience change at an atomic level are considered radioactive. Decay is the process of change at atomic level. So the substances are radioactive. Decay is the process. Reactivity is a tendency or processes of substance that are radioactive. They sort of overlap a little bit. And then we can go through and talk about units of radioactivity. Now, when it comes to radioactivity, one of the first units was something called a gray. A gray is a joule of energy absorbed per kilogram of tissue because it has to how it affects tissue. And then a rad is 0.01 joules of energy absorbed per kilogram of tissue. Not all emissions have the same effect on biological tissues because some have more energy. So we come up with something called an RBE, a relative biological effect. 1 RBE is equivalent to a beta emission, where 10 RBEs is a gamma emission. Gamma is much more radioactive and effective in that way. All right, now we're going to talk about particle emissions. These are the types of material. Now, I talked about this last year, and I'll go more specific. But when we talked about, these are particles that are combined in a bombardment or removed, emitted to cause changes at an atom level. Now, the first one is called an alpha particle. And when we first started coming up with these, we wanted to sound really scientific, so we started using the Greek alphabet, alpha, beta, gamma. But then eventually we said, this is silly, let's just call it what it is. So an alpha is 2 protons and 2 neutrons. When we do something later called transmutation, this is the way we represent a helium nuclei. That's an alpha particle. Beta particle are what are left. They're the electrons. That's a symbol for it, because again, old system. And we represent it in transmutation as electron, E0 over -1. We then have gamma. Gamma is pure energy. We talked about the binding energy last year. That's the energy that holds the nucleus together. We're going to talk later about how that process can be calculated this year here. Then we start getting into the new understanding. A neutron or a neutrino is N1 over 0. We don't have, it's just a neutron. A proton, again, is just a proton. It's H1 over 1. Then we have something called a hydrogen nuclei, a positron. It's the same mass as an electron, but the opposite charge. So instead of being E0 over -1 for like a beta emission electron, it's going to E0 over +1. And these are what we use in something referred to as transmutations. Now, transmutations are processes of nuclear change in reaction form. Now, I'm going to go through it real quick, like we did discuss it last year in Chem 1. So if you want to go back into my playlist, Chem 1 Day 171, I have a full video about transmutations and how they work. All right, so here's what we're going to do. We're going to take a reaction. This is one of the reactions that are really important to go through. This is carbon-14, carbon dating. All right, now, how does this work? Well, we're going to generate what's called an emission. What do we mean? You see, when we do this, we're going to generate an electron. So if we add a beta emission, okay, so 7 minus 1 is 6, so those numbers are the same. So the numbers on the atomic numbers, the number of protons, need to be the same on both sides, and the atomic mass, the numbers of protons and neutrons, need to be the same on both sides. So 14 plus 0 is still 14. That's good. 7 plus -1, that's 6. That's how that works. All right. Now, we can also get what's called a bombardment, where we put the particle in. What we're going to add here? Well, we're going to look the same thing. 37 to get 36. I need to also add a beta. But this is going to be a beta bombardment, as opposed to the first one was a beta emission, okay? So we're going to do these in such a way, using those 4 particles, alpha, beta, neutron, proton, positron, phosphide particles. We're not going to see gamma because gamma is just released as pure energy. All right, so let's try what's called a series. It's where one transmutation results in further transmutational series. And you'll see down there, eventually, most of them end up at lead. All right, so let's take the first one, 92. Well, we add the 92 to get 90. Well, the only thing you can do is take 2. 2 plus 92 is 90, and 4 times 234 is 238. Once we get this one, this is my product. This becomes the next reactant in the next transmutational series. So thorium becomes down there, thorium 234. What am I going to add to 90 to get 93? Well, of our 5 particles, there is none that...
Actually, what do I add to 93 to get 90?
0 over 3, but there is one that is 0 over negative 1. So I can take 3 of those. So negative 3 and 93 is 90. Then we take that uranium-234, we want to slide it down. Now what can we add to 90 to get 93? Well, that's 3. What would add 231 to get 234? 3, but there is no 3 over 3 of those 5 particles. So we're going to use the proton, H1 over 1, and make 3 of those as well. And then that thorium comes down for the next reaction. And then what am I going to add to 92? I'm sorry, 88 to get 90. That would be 2. 227 to get 231. That would be another alpha, He4 over 2. And then work our way down here eventually to get 2 for 92. That's 2. 207 from 211. That's also. And if we want to name these, we have alpha, beta, proton, alpha, and all of these are emissions because they're on one side. All right, awesome. Now, last thing we're talking about is actually something we talked about this year and last year. It's reactor decay. Reactor decay, these are 2 reactions here. So these are the process we go through. These are first order reactions. We talked about reactor reactions here. AT is the amount of radioactive isotope that remains. AO is the amount that we originally had. E is the natural log base. T is time. K is a reaction constant, which is defined by 0.693 divided by T1/2. If you go back to first order reaction, you'll see these exactly the same. Alrighty, so let's take a problem. Determine the amount of radioactive material that remains after 2.500 years if the half-life of radioactive isotope is 321.65 days. The amount of original radioactive substance is 123.8995. Now, remember, when we do this, we use this reaction to find AT or AO. We use this reaction to find negative K, or K or T. All right, that's great. So we use that one because we don't know AT. So we're going to use that first equation. If we're looking for K or T, we'd use that other equation. AO is 123.8995 grams. K is 0.693 over T1/2. And from the problem, we see that T1/2 is 321.65 days. We multiply that through, we get 0.00215545 per day. And then the time is 2.500 years, but we need that in days. So 365.25 because of leap year days is 1 year. Multiply through, we get 913.1 days. All right. So plug the values in the equation, 123.8995 grams times E raised to the negative 0.00215545 per day times 913.1 days. My days are going to cross out. We multiply that through. We get 17.33, so take our calculator, 123.8995 times parentheses E raised to the parentheses 0.00215545 times 913.1 parentheses equal, and you should get 17.33 grams. All right, that's our answer. All right, let's try one more again. These are also review from last year, looking at day 173, 175 in Chem 1. All right, so calculate the half-life reactor isotope. If it takes 21.245 days to go from 19.567 grams to 13.788 grams. So I want you to pause it right now, work through it. We're going to use that second equation, ln of AT over AO is equal to minus KT. Work through it. Any questions, let me know. ltswpd@gmail.com. Remember, like, subscribe, share. Any questions, let me know. Here we go. there's all the work. So we're gonna solve for K here. When we solve for K, we get 0.016477 per day. And then we're gonna flip the terms to solve for T1 half. T1 half is 42.059 days. Awesome. That's it. Hopefully not too bad. Take care. God bless. Bye.